Hello. So the last two assignments, which I gave out last night. Assignment 4 is a little bit easier about determinants. And assignment 3, this one is more difficult. Later on, I will talk about it. Let's talk about the easier one first. This one, although almost all of you completed correctly, I still want to mention the meaning behind each exercise. For question 14. Question 14 asks you to expand and find the determinant of A through the second row, I think. This is through the second row. Expand according to the second row. And the answer is -9. And part B, expand according to the third column. And the answer is -9. Now this exercise was given to you so that you can have a deeper understanding, or maybe a deeper impression that a determinant can be found through these ways, although different expansion but same result. Because during the lesson we didn't prove it, like mathematically prove it. This provides another piece of evidence. For question 18. Question 18 asks you to prove for determinants of this and this, they are equal. Now the process is not difficult, but this reveals something more profound behind. Now you can notice that both of these two determinants, they are equal to AD minus BC, which is the determinant of ABCD. So I can further conclude from this question, I can further conclude that determinant of ABCD is equal to, however I make it smaller. What do I mean? That means I keep the first column, and then I use the second column minus the corresponding elements from the first column. An example would be, for example, this is 5, 4, and this is 5, 6. I can simplify by saying, oh, this is 5, 4, but I'll reduce the second column by 5 minus 5, which is 0, and 6 minus 4, which is 2. In this case, it's easier to, because this one is easier to compute. It has a 0 here, so this one is 10. You know what I mean? So you can reduce one column if you see fit in this way. Similarly, you see this result, the right-hand side is also equal to AD minus BC. That means we still have this ABCD, the determinant, is equal to, if I keep one of the rows, AB, and I reduce the second row, which is C minus A, D minus B. An example would be, let's say this is 3, 7. This is 3, 8. I can reduce it by keeping the first row, and I reduce the second row, which is 0, 1. And this one is easier to compute. Now this result from question 18, this result in the past syllabus was included as one of the properties of determinants. But from this year, I think from last year, I don't remember exactly which cohort, but recently we have reduced the syllabus, so this property can only be observed from the homework assignment. But it's very convenient to use though. Okay. Question 19. Question 19, it says that this and this are equal. Now, if you observe this, you will see that there is a factor in the second column. And then afterwards, the factor is taken out, and this is another determinant. What does this mean? This means if you see a factor in a column, later on you will see that if you see a factor in a row, you can take it out so that you can reduce the elements inside the determinants. For example, in calculating determinants, this is what you can do. This is 1, 2, and this is maybe 30, 40. You can reduce it by taking out a factor 10 from the second column. You will still get the same answer. Now this can be done through a column or a row. You can also take out 10. Okay, and this property applies to all determinants, not just determinants of degree 2. All determinants, including degree 3. Okay, so that's 19. Something that you can use. If you can remember them, I recommend that you have a little bit something extra in your pocket. It's not necessary though. It's not. You must do it. But something new. When you do this, when you do something in your homework, there's something you can learn. Like I said, I think starting this chapter, I mentioned that everything that you do in this chapter, you must learn something from it. Question 25. I think this is an easy question. Not much to learn though. Okay. And then question 27. Also, we'll talk about this later. Question 26. There is something, but it's difficult to explain right now. So that is the last assignment from the summer holiday. Now let's go to the previous assignment. The previous question, these 4 questions are quite challenging. It is. So I'm very happy to see most of you are spending time on it, and you're doing very, very well. It's just a small problem, and I just need to talk about a very tiny issue. Now, for question 25, it's hard to understand the intention of this question. Let me explain then. I have copied the question here so you can read it again. So for question 25, if a matrix is given, In this case, it's a 2 by 2 matrix. Then we can define a function called TR. Now here, TR means trace. The name of this function is called the trace of X. We define, that means, oh, just call this trace. What is the trace of X? That is the sum of the principal diagonal. In this case, P plus S. Okay. Now, why do we call this the trace of X? I think upon finishing part A1 and part A2, you should notice the importance of this function trace. You can see that if I add A to B, if I add A to B and then find the trace, it's equal to I find the trace separately and then add. Also, you can see that if I multiply AB, although we know that AB and BA are not necessarily equal in the world of matrix, most of the time they're not equal. But when you find the trace of these two, they're equal. So upon finishing these two exercises, you should know that the reason we call this the trace is because it can help us find something. It kind of like, oh, these matrices, they leave a trace behind them that you can find a little bit clue after the operation. Because the addition, it does not change the trace. And also swapping AB and BA does not change the trace. That's the meaning of trace, basically. Okay, now the proving, you can do this. You have to go deep into the elements. So you can let A be this and let B be this and find A plus B. And after you find A plus B, you can see that, oh, the trace are equal because this is the trace, this is the trace, and this is the trace of the sum. So they are equal. And for A2, you have to actually do A, B, and BA separately. So you do this, A, B, and BA. So this is the trace. The multiplication must be done by you. So you can see that the elements are not equal. If you compare this element and this element, they are not equal, but the trace are equal. Okay, so that is how you do part A and part A1 and 2. Part B, so you have learned that this is what's special about trace. So trace can help you identify something. Basically, it's some evidence that you have in your mind. Can you find P and Q separately, such that PQ minus QP is equal to this simple matrix? And the answer is no. Now some of you don't know how to explain. This is what you think. Now since we know trace equal trace A plus trace B. I want you to not very difficult, but I want you to think about if that trace A minus B equal trace A minus trace B. I don't think this is very difficult to prove. Okay, because this is a minus here. This is a minus. So from the first part A1, you must think about if this is true and briefly mention this is true. Okay? It's obviously true. Okay? Now, after you mention this is true, you can say that, oh, the left-hand side, because trace PQ equal trace QP. Therefore, the trace of left-hand side must equal 0. But the trace of the right-hand side equal 5. So I don't think the left-hand side can ever equal to the right-hand side, although I have no knowledge of P or Q. Is it fine? So it's not easy. It's not easy. From the addition, you must think of the subtraction. And then think about the trace of both left-hand side and right-hand side. This is the standard answer. Okay? This is the standard answer. Hence, it is impossible to find P and Q such that PQ minus QP equal to this matrix. Okay? After 25, I want to mention 26. 26, you must show this step. You must show. You cannot say, oh, the left-hand side equal to the right-hand side directly. Some of you are doing that. That's not a proof, right? Now for 28, you have to show this step. When you multiply a to the power k to a, you must show this and show this, and then to the right-hand side. This step must be shown. Because you have to show the actual multiplication and to verify the result is equal to the right-hand side. You cannot say, oh, this is equal to the right-hand side directly. You cannot do that. Moving on. Similarly, you have to show this. And for this to equal to the right-hand side, the easiest formula to use is the compound formula, but use it backwards. Now, you look at this. This is is it equal to co minus sine? Isn't it? You use it backwards. You use this way, it's an expansion. For this way, if you use it backwards, then you can reduce it. Okay. Now this result, actually, for question 29, this result is very interesting. Now for an equal, a to the power n equal this is actually very interesting. I think in the future, we will come across this matrix very often. You remember what A is? A is this. This is A. This is A. This is A to the power n. So basically, this is a very interesting matrix that you can easily multiply. Because the power is equivalent to increasing the angle. Well, this is the matrix about angle, one angle. This is just to increase the angle. The multiplication is equivalent to increasing the angle. Very interesting. We'll come back to this in the future. And a direct use of this is that you realize these values, 1/2, √3/2, are the trigonometric ratios of 60 degrees, in this case, 60 degrees. You must realize that first. And after that, you can change the power of the matrix to the increment of the angles. Change the angles, increase the angles, and then you can find the value. Otherwise, there's no way to do it. You cannot possibly multiply this so many times. It's just not possible to do. Okay? So that is the 2 assignments. For assignment 3, some of you need to do correction, and I remind you, although it's from the summer holiday, I want you to do the correction still. And don't give up too quickly. If you spend time, you will see yourself improving every day. Now, I'll give you 1 minute to download this file in the Google Classroom. Okay. Now this is the last part. I think I promised in the past, we will study the division of matrix, and this is where we study it. It's not called division, it's called inverse. We borrow the name from the inverse of a number. For example, now in the past, if I have a number, let's say it's 5x equals 7. I know that we also learned division, but let's say we do not use the concept division. Let's use the inverse of 5. Now, what does that mean? This is the inverse of 5. So if I have the inverse of 5, which is 1 over 5, then I can multiply and then get x. Okay. So similar thing with the matrices is that if I have A times X equal B, what I'm interested is not to how to define the division. I do not say or define what is B divided by A. There's no such thing. Or B over A. There's no such thing. I'm not interested in defining a new operation. I'm interested in finding the inverse of A. If I could find the inverse of A, let's say I call it A inverse. If I can find it, and I will be able to multiply. And then these two, because they are inverse of each other, their product should equal to I, which is the identity. And I times X should equal X. So I want to make sure that for each matrix, in this case, we're not discussing every matrix. It's just square matrix. Now, for these rectangular matrices, we don't have a very good method yet. But for square matrices, I think we were capable and very ready to find the inverse. So look at the definition now. So for a matrix, which is a square matrix, it can be 2 by 2, it can be 3 by 3. In our textbook, we do not discuss 4 by 4 or above. So A is a square matrix and I is the identity matrix. That means I either is 1, 0, 0, 1 or 1, 1, 1. Like that. Of the same order. So A and I are the same order. So there is a matrix B such that A times B and B times A, they're equal and both of them are equal to I, the identity. Okay, now if we're able to find it, if we're able to find this matrix B, we will say that A is non-singular. If we're not able to find, then we say A is singular. For example, I can give you a very easy non-singular matrix, say non-singular. For example, 2, 0, 2, 0. This is non-singular. Because I can find something, multiply this equal I very, very easily. See? This one is non-singular. This one is non-singular. Now, for singular ones, easy. 0, 0, 0, 0. No matter what you multiply, you cannot get identity matrix. Right? It's not just this one, there are more. Is it fine? About the name, non-singular and singular. It's quite confusing because it's not a grammar term, like singular and plural. It's not talking about something as alone or with many. The word singular has a positive connotation. It describes something awesome and magical, which is these ones. In mathematicians' world, they are more interested in the in the singular matrix, because these ones maybe a lot of mystery and new discoveries are hidden. In fact, people are still studying this even today. Now, the non-singular ones, in other words, I can call it trivial, means ordinary and very plain and nothing outstanding. These ones are we are trying to learn these ones, the non-singular ones, because in our textbook, these ones you can easily find the inverse. Okay, so that is the word singular. Now about the notation just now I mentioned already. If B is an inverse, then it's notated as A -1. I don't say this is A to the power. I just call it A inverse. It's not a power thing. It's not an index. It's an inverse of A. Now, if A is an inverse of, if B is an inverse of A, you can also say A is the inverse of B. Okay. Example. Now, these examples are extremely easy. So we won't be spending too much time on it. You just have to understand. So how do you verify a matrix B is an inverse of A? So far, we don't have any other means. We just have to check if A times B equal I and B times A equal I. Then let's do the multiplication. Remember, 3 times 3 plus negative 2 times 4. This one is negative 4 times 3 plus 3 times 4. This one is 3 times 2 plus negative 2 times 3. This one is negative 4 times 2 plus 3 times 3. And it's equal to the identity. You doing it backwards. 3 times 3 plus 2 times negative 4. 4 times 3 plus 3 times negative 4. 3 times negative 2 plus 2 times 3. 4 times negative 2 plus 3 times 3. So that is it. Fine. So both of them are equal to identity. So B is an inverse of A. Now here I want to mention it's a little bit too, I think it's quite advanced, but if you are interested, you can take a note. Now some students are asking that if I found A times B equal I already, is it possible that B of B times A is not equal to I? Now I can tell you that this is a result that cannot happen, but it requires further knowledge to understand why this cannot happen. So in reality, if A times B equal to I, then definitely B times A will equal to I, but it's not easy to prove though. It's also not in our textbook. So in our practice, you will check both. In other textbooks, if you go to university and then you choose a course and a math course, and sometimes you will see the textbook will only be checking just one multiplication, and that is allowed. In future study, that's allowed. Right now, check both. The quick practice the same. You check both. Now tell me when you're done. Raise your hand when you're done. Okay. Sorry, I shouldn't say it so negatively. That in fact, I think with your ability, you should be able to prove it. So try this if you can prove it. Prove that if A times B is equal to I, then B times A must equal to I. You can try. You can try, because I remember in the past I've done it before, but it's not easy. But I think with your ability, you should try or find out how this can be proven. Okay, let me know. Let me know your findings. Okay. Now the next question, I think it's a better way of finding the inverse, although it's heavily based on the given condition. You see these questions, the quick example, quick practice, these questions, the inverse is given, you only have to verify. And this one inverse is not given, you have to find. You have to find, but something else is given. You have to show this equation. Let's show it then. To show any equation in matrix, you don't have to think a lot. Most of the time, it's just pure muscle work. For this one too. It's 2, 2, 1, 3, 3, 2, 1, 3, 2, 1, 1, 1, and 3, 1, 1, 1. And this is 7, 3, 9, 4. Okay, so this A is 2, 1, 3, 1, and that is 7 minus 8 plus 1, 9 minus As why are they not equal? 9 minus 12 plus 0. Am I wrong? Is it 9? Is it 12? Sorry, I was wrong. Made a mistake. It's a typo. Here it's 2. Big 2. Okay. Sorry, I made a mistake. Does not work. Let's redo. It's 2, 2, 1, 3, and 3, 2, 2, 3, and 2, 1, 1, 2. 3, 1, 2, 2. Sorry. 7, 12, 4, 7. 7, 4, 12, 7. So 7 minus 8 plus 1, 12 minus 12 plus 0. This is 4 minus 4 plus 0. And this one is 7 minus 8 plus 1. And it is equal to 0, 0, 0, 0. In this case, a dark 0. Okay? So that is to verify. And this is very important information. From this information, we'll be able to find the inverse of A, although we're not taught. We just have to use the definition of the inverse. Now, because we know this is equal to 0, now here 0 must be bold, dark 0. Therefore, I know that 4a minus a squared must equal to I, right? Therefore, if I take out a, I will have 4i minus a. And also, if I take out a on this side, I also have 4i minus a. So from this multiplication, 4a minus a squared equal I can find another matrix in this case. It's 4i minus a. Multiply a on the left or multiply a on the right, both equal to the identity. Therefore, according to the definition, this matrix 4i minus a is my inverse. Now here I'm going to use 4i minus a and to get my inverse. Okay, it looks like we didn't verify, but trust me, this matrix is the inverse. If you don't believe me, you can multiply a and see. Now let's do the quick practice. When you are done, you let me know.
Hi, Ms. Chen. Sorry, I have a question for this part. May I know, can I not write I in the bracket, but instead I write 4 minus a as the inverse of a?
It's a very good question. Do you mean here? No, you cannot write 4 minus a because 4 is a value, it's a scalar, and a is a matrix, and we do not know how to do the subtraction between a value and a matrix.
Okay, thank you, Ms. Chen.
You must write 4i. Okay? Okay, girls. Now the part A, I think you can verify. Part B, starting from here, because I already took out A. So this value, in order to get I, you must multiply 1/3. Please don't say divided by 3. It's just multiply 1/3. So this is the inverse. 1/3 times A minus 2I is the inverse. And then the final answer is from the textbook. This is the final answer. Now in the final answer, you can see the coefficient 1/3 can be put in front. You can also say it's minus 1, 2/3, 0, and 1/3. That's also okay. Is it fine? Let's move on. So that is the part about the definition of inverse. And we can find the inverse heavily based on the given condition. Sometimes it's given to you directly. And for this example, it's given to you through an equation that you're asked to prove. But in reality, we don't know how this equation is obtained. But hold on, hold on. In the end, we will review how to compute the inverse all by yourself. The next page, then this page is very, I think it's the most important part in today's lesson. And for those who are absent today, I hope that when you're watching this video, you must take notes. This one, we will investigate the properties of the inverse. And to see that if we have found inverse, how can we use it? And these are all valid results. I will prove these one by one in today's lesson. It's a very good practice. If you want to understand the algebra, see how the algebra part of the matrix is done. Instead of, oh, we just learn the definition, we just learn how to do it. That's not the algebra part. The algebra part is this, the properties, because we're using symbols basically. Now, how do we use symbols to prove each one of them is true? The first one. The inverse of A is unique. Let B and C be the inverse of A. To prove something is unique, I will assume that there are two. Suppose it's not unique. Because A times B equal I. Right? A times B equal I. And then C times A, B equal C times I. I just multiply C on both sides. That means C, A, B equal C. But in this part, I'm using the associative property of matrix. Now in matrix, I cannot swap the order of the multiplication, the position of the multiplication, but I can group them. I can choose to do this first, as long as I don't swap the order of CAB. Now it's CAB, it's still CAB, it's just I do CA first. Okay. And because we know CA is I, so IB equals C. Therefore, we get B equals C. So for any two inverse of A, B and C, they're equal. Therefore, the inverse of A is unique. Meaning I can't find two. If I find one, I'm lucky. Okay. Part B. The inverse of inverse is A. By definition, A times A inverse and A inverse times A equal I. Okay, that's the definition of inverse. And because of that, if we're looking at this as our matrix, we will know that A is the inverse of A inverse. We know that, therefore, A is the inverse of A inverse, because A times A inverse equal I. Therefore, A inverse equal A. Moving on. 3. Lambda times A. Lambda is the value. Lambda is a scalar value, is a number. Lambda times A inverse is 1 over lambda times A inverse. Because lambda times A times 1 over lambda times A inverse equal lambda times 1 over lambda times A inverse equal 1 times I equal I. Now this is my first variation to see if these two multiply equal I. I will also check the other side. 1 over lambda A inverse times lambda A equal, that this time I swap them and to see if they multiply still equal I. And then 1 over lambda times A inverse times A, and then I can group them again, and that is 1 times I equal I. So after checking, we know that the inverse of lambda A equal 1 over lambda A inverse. Now perhaps the most unfamiliar one for us is that I can multiply the number first. Remember the scalar in this multiplication, the scalars can be done first. Okay, and then we can multiply the matrix. That's what we can do. That's what we can do. As long as I do not swap the matrix, I can put the whatever number, because number can be multiplied in. Let me find let me find it. I don't know exactly where now. In the textbook. Not these ones. Now this property is on page 10. I'm sorry, not page 10. Page 21. This one, D. Lambda A times mu B is lambda mu first, and then AB. So transfer that to our case here. It's lambda and 1 over lambda. They can be done first. So that is verified. Now this is very interesting. This is very important though, because sometimes I need to find the inverse of 2A. And you know that it's 1/2 times A inverse, basically. You don't have to do another inverse. The numbers can be taken out, basic, in doing the inverse. D. The what's the name? Transpose. Transpose inverse is the inverse transpose. Let's find out. D. Let's say the transpose times the inverse transpose. What is it equal to? In the past, we know that A transpose B transpose equal B A transpose, right? That's the one we're using. So A transpose A inverse transpose equal A inverse A transpose. In this case, equal I transpose equal I. Now, how about I swap them? I swap them the same. A inverse transpose A transpose equal A inverse transpose. That is also I transpose equal I. Therefore, I can say, oh, these two matrices, they are inverse of each other. That means AT inverse equal A inverse T. Is that fine? Now you can taste the algebra part. I'm manipulating the letters using what I know. Now some of you are used to that, but it's new. For you, it's new. You must get used to it though. E. How do I prove that AB inverse is B inverse equal A inverse? What should I verify? I should verify if AB times B inverse A inverse, if it's equal to I. Let's try if this is equal to I. Now first, as long as I do not change the order, I'm fine. So I will make sure it's A, B, B inverse, A inverse in the same sequence, but I will do this first. That's called the associative law. And that is equal to A inverse. An A inverse, you can do this first. That's A inverse. So that is equal to I. So the first one is checked. Now let me ask you, what should I verify next? Trần Hey.
I don't really know.
Now, you need to verify. You see, now you say this inverse is this. So you must verify if this multiply this equal I. Also, you need to verify this multiply this is equal I. So the next one I need to verify is this value of this matrix times this matrix and see if it's equal to I. Now, if this multiply this equal I and this multiply this equal I, both equal I, then they are inverse of each other. That is what we want to prove. You know? Now, maybe this is too much. You see, if I want to say X inverse equal Y, if I want to verify X inverse equal Y, I must check XY and YX. The same applies here. It's just more. The letters are more. If I want to say AB inverse is B inverse A inverse, I need to multiply AB with the right-hand side. In whatever order, left multiply or right multiply. So here we still have to do the right multiply. So in this case, I will keep the order. And then I will associate the middle. And then I will associate these two. And this is equal to 9. Okay? So I found that, oh, these two make, although they look scary, this is a huge thing, but remember, this is a matrix and this is another matrix. So these two matrices, imagine this is X, this is Y. This is Y, this is X. So X times Y equal I. Y times X equal I. That means the inverse of X equal Y. Now 1 minute to write this down. 1 minute to write this down. Okay. Now I suppose you've written down, because the next one I'll ask you, if I want to verify a to the power n inverse is a inverse to the power n, what should I check? If you understood D and E, you should be able to answer. Okay, now let me ask. Iris, what should I check for F? Iris? Your microphone is broken. Okay. So who do you think should answer for you? Maybe Cassandra? Cassandra, do you know which two? How do I check if A n inverse equal A inverse n?
Do we check if a to the power of n times a inverse to the power of n equals I?
Correct. Now, basically, you see it's X inverse equal Y. Okay, X inverse equal Y. You need to multiply X with Y. Let's check if this is really equal I, then okay. But it's not so easy though. Why is this equal I? Now you don't use the algebra of numbers, okay? Any like index law does not work here. You cannot use index law. You must use the multiplication of matrix. So what we know about this is that AN is A. Basically a lot of A's. And this one is A inverse, a lot of A inverse. Okay. Now what we do is that we make them clash in the middle. That is to do this first. Now after you do this, it's A, and then n minus 1, do you know? This is I, this is I. And then you have A minus, oh, not A minus, A inverse, also n minus 1. And then you make them clash in the middle again, and then you get n minus 2. You know what I mean? So in the end, you will get A inverse, and then equal I. So that's how you verify A to the power n and times A inverse to the power. Now after this, what should I check again? What else should I check? Lattice.
For G, check
F.
F for check if the A inverse to the power of n times A to the power of n is equal to I.
You check this and then you flip them, you swap them, and then you do it again. Same method, okay? And then you will verify all that is true. Okay, I don't have a space to write. So that's F. Now if you see D, E, and F, they have something similar. Now we're doing the same thing. Now for C, it's also the same. If I want to find out if something's inverse is another thing, I check whether or not they multiply equal I. Now for the last one is not about the matrix. The last one is the determinant. So determinant of inverse A and A, they are supposed to be reciprocal of each other, now also called the inverse of numbers. So this is true because we know A inverse equal I. And we also know determinant A inverse equal determinant of I. We also know that determinant of A and determinant of A inverse equal 1. Now, remember determinant of I equal 1. So this is 1. Therefore, determinant of A inverse and determinant of A, they are inverse of each other. In numbers, we call them reciprocal. We don't use inverse that often. I suppose we do. Reciprocal of each other. That means if determinant of A equals 3, then determinant of A inverse equal 1 over 3. These are numbers, not matrices. Is it fine? So it's all proven. How often are they used? At least once. I think in difficult questions, you have to be able to use all of them. In a easier exercise, like the homework, maybe just one question using one property. But in difficult questions, you may have to use a few of them together. Is it fine? They're all proven. Do any of them, does any of them look strange to you? Maybe this one, because a lot of times people will think AB inverse is A inverse B inverse, but that's not true. It's not true. It's not equal to A inverse B inverse. It's like a distributive of the index. It's not. You mustn't like equate this to the index law. It does not apply all the time. They look very similar. Sometimes they operate the same way, but not all the time. In this case, you have to swap them. And that this one is similar to the transpose, right? The AB transpose equal to B transpose A transpose. I suppose that is something that you can relate it to. Okay. Look at the examples. The examples, I'm gonna speed it up. First, this is 3 by 3 matrix. And to show this is inverse, I don't want to spend time during the lesson because you can do that yourself. To show, you have to multiply. This is P, this is a given one. So multiply it left and right. Really doing it. Therefore, you can conclude. Now, it takes a lot of time. I know, in your work, it takes a lot of time, but during the lesson, we can speed it up. Now for Q, the same thing. Left multiply, verify, and right multiply. And then you have the conclusion. This is the inverse. Only after the 2 verification, now you can conclude. Okay, now I want to talk about the last one. Part B, find this. Now, obviously, I'm not gonna, let's do it step by step. I just write down everything and then do the multiplication and then do the inverse. I'm not gonna do that. Not gonna do that. I'm gonna use the inverse property. So here's how you use it. The inverse property, PTQP inverse. PTQP inverse. You don't have to do it step by step. You can use the property. For example, you can use this is 1 and this is 2. This is P, T, and then Q, P inverse, like this. And then you can do you can do Q, P inverse, P, T inverse. That is AB inverse equal B inverse A inverse. Okay. And for this part, you can do it again. For this part is P inverse Q inverse. And then this one is PT inverse. Okay. Now for this one, P inverse, that's P. Q inverse, you cannot simplify, that's Q inverse. But PT inverse can be P inverse T. And then you do the substitution. And then you simplify to get the answer. You know what I mean? So a little bit simpler, instead of, I mean, you do this, that's way more. If you do this, it's way more. Okay? So that's the answer. Now you can do the practice. I think after this, we're almost done. Let me know. Okay. I see that you're done. If you haven't done, can you look at this answer? So this is how you do it. So you change it to A, B inverse, A inverse transpose, and then you multiply. Now do not put the 1/5 inside in the multiplication. You just leave it outside, and then in the end, you can multiply it inside. Otherwise, the multiplication is too difficult. Okay? So if you've done this, this is the algebra part. The algebra part, and then this is the substitution part. Substitution part, some of you have a program in your calculator, so if you have it, you can use it, this one. But each step you must show. I think that's all. That's all. If you have a question, you can stay behind. Since Sophie, you can stay behind, you have a question, and the rest you can go.
Hi, Ms. Chen. Sorry, I like last time I asked you if I had have the answer for topic 6, but I don't think I can find it in Google Classroom.
What? Say again?
The answer for our summer homework M2 topic 6, the solution. I'm not sure why I cannot find it in Google Classroom.
Isn't it here? No.
In the old one or in the new one?
Old one.
Oh, I think it's up to topic 4 only.
Not here.
I can't find it.
This is 4, 4. This is 4. Why do I
Yeah,
have
but
2 4s? Why do I have 2 4s? Is this 6? Is this 4? Okay,
yeah,
I'll give it to you today.
okay, thank you very much.
5, 6, 7?
5 and 6 only.
5 and 6. I only uploaded 4. Is that what I mean?
Yeah,
Is
yeah, yeah.
it at the end? Is it because it's at the end? No, it's still.
No, I think, yeah, there's only 2 4. Yeah, thank you.
Okay.
Thank you, bye-bye.
Hello, Ms. Chen.
What is your question again?
I don't really understand when, like, in what scenario the trapezium rule will give an overestimation and an underestimation.
Oh, it's actually very simple. As long as you know what the graph is. Wait.
Thank you, Ms. Chen.
Let me turn off the